Hi, welcome to the Chapter 9 lecture. This week we'll be looking at the topic of climate and climate change. Okay, so by the end of this chapter, hopefully you will understand how the troposphere and stratosphere differ, be able to discuss some of the factors in natural climate variability, explain the greenhouse effect and how it is changing our climate, be able to discuss how we know the nature and cause of recent climate change, be able to list some effects of climate change, and then also list some strategies for minimizing global climate change. Here's a quote from the International Energy Agency in 2010, and they stated that the next decade is critical. If emissions do not peak by around 2020, the needed 50% reduction by 2050 will become much more costly. In fact, the opportunity may be lost completely. And we'll take a look as we go through this chapter on our current emissions and strategies and how those are working, and then we'll talk about whether we coming into the year 2020 are meeting that goal that they said was necessary to reach by 2020. Your book discusses a case study on is weird weather the new normal? And as you can see from this graph here, it shows the United States in the year 2011 having severe drought in certain parts of the country, mainly in the drought was mainly focused in Texas, as you can see here. So there was exceptional drought in this area in 2011. And for cattle ranchers in 2011, it was a terrible year. It was the hottest and driest year observed since record keeping began in 1895. They had more than 90 days with temperatures over 100 degrees Fahrenheit, about double the normal number. Lakes and streams and watering ponds dried up and disappeared. So did the grass on the pastures. So it left the cattle with nothing to eat in the pastures. And so drought also meant no harvest of hay, which was critical for the winter feed. And by the end of the year, Texas ranchers were forced to sell or slaughter 1.4 million cattle, or roughly 11% of the state total. And because Texas is the nation's largest producer of beef cattle, the impacts were felt in beef prices across the country. And this drought was extreme even for a region that is accustomed to heat and drought. But the state climatologist has warned that these dry conditions could last for a decade or longer. Much of the South and the West have seen similar extremes, and the question really becomes, is this just weird weather or is it part of a larger pattern? And this is the question that policymakers and scientists and the public are all asking. In a complex and rapidly shifting system like weather, most of us tend to see data selectively focusing on pieces of evidence that confirm our expectations. For some observers, they'll look at several bad years of drought that's confirming proof of human-caused climate change. And for others, they'll see a string of bad years as just simply a variation in a complex system we called weather. And so what we hope to look at in this chapter is how do we know what's really going on? So we know that global average temperatures have increased. If we look at data from going back to the 1880s to the present, we can see the yellow is the annual mean temperature. The red is the 5-year mean temperature. So that really the red is just sort of smoothing out the data points that we see in the highs and lows in the yellow here. And then the black line is our carbon dioxide concentration. So we can see that over the past little over 100 years that our CO2 concentrations have steadily gone up, and our average temperatures have steadily gone up with that. So the temperatures bounce around a little bit more, but in general, we're seeing this overall trend of our CO2 concentration is going up and our average temperature is going up over the past 100+ years. Let's first, before we get into a more detailed description on how climate is changing, let's make sure we understand the difference between weather and climate. So at the bottom here, the quote tells you weather tells you what to wear on a given day, climate tells you what wardrobe to have. So weather is a state of atmosphere at a specific time and place, and variables include temperature, humidity, cloudiness, precipitation, wind, and speed direction. And climate is weather of a given location averaged over a period of time. It includes extremes in weather, behavior observed during the same time period, and it Climate looks at how the weather behaves over relatively long periods of time. So when you talk about weather, you might be talking about the temperature for the day, how humid, how cloudy, how wet, how windy. So things in a very specific time period. Climate is looking at the overall general trend of how the weather behaves in a region over a long period of time. The first section for this chapter is section 9.1, what is the atmosphere? And the Earth's atmosphere is the layer of gases that surround the Earth. So you have the Earth here, and then surrounding the Earth, you have this layer where gases are present. As you go into outer space, you just have emptiness and no gases present, but surrounding our planet, you have these layers here. We'll get into these layers on the next slide, but each of these layers has different gases within it. And the Earth's atmosphere consists of gas molecules, mostly nitrogen and oxygen, and a variety of other trace gases that are relatively densely packed near the surface. You're going to have a lot of gases present in the atmosphere close to the Earth. And then as you go out further and further away from the Earth, the gases become more and more spread out. There are also minute, tiny particles and liquid droplets called aerosols that are also suspended in the air. So you have this layer that has gases and other tiny particles such as water droplets, and that makes up our atmosphere. There are 4 distinct zones in the atmosphere. There's the troposphere, the stratosphere, the mesosphere, and the thermosphere. And these zones are differentiated based on the temperature. So if you follow the temperature line here, the troposphere is this temperature range in this region. And then as you get into the stratosphere, the temperature changes as you go higher and higher in the atmosphere. It actually becomes a little bit warmer in the stratosphere. And then as you go into the mesosphere, the temperature then goes back to being colder as you go up higher. And then in the thermosphere, the temperature then becomes warmer as you go higher. So there's these different temperature patterns, and that's how they distinguish the different layers in the atmosphere. Now the layer closest to the Earth's surface is called the troposphere, and this is where all of our weather that we see on Earth occurs, is in this region of the atmosphere called the troposphere. So that's where the daily temperature changes, the wind, precipitation that we call weather, all occur. Now the reason that we have all these changes that we see here are there are different currents, so air currents blowing around, what we call convection currents. You can see here in this figure from your text the airflow on Earth. And so as you start at the pole here, airflow is generally winds are blowing to the south. As you go from the 30th parallel to the 60th parallel, you have these westerly winds blowing the wind to the west. As you go below the 30th parallel toward the equator, you have the trade winds blowing the air to the east. Air also gets circulated on Earth in these vertical currents here. So air circles along, goes straight up, and then it goes up into the air and then comes to the south and then goes back down to the Earth. So you get these currents moving both vertically blowing the air around and then east to west. And these help drive our weather that we see on Earth. And again, this is in the troposphere, that layer immediately above the Earth. Now, the atmosphere captures energy, but selectively. So the sun supplies the Earth with lots of energy, especially near the equator. Energy is heat, and so the sun is supplying energy, heat in the form of energy to the Earth. Of all the solar energy that reaches our atmosphere, reaches our outer atmosphere, a quarter of it gets reflected by clouds and atmospheric gases, just gets reflected back out. A quarter of it gets absorbed by things like carbon dioxide, water vapor, ozone, methane, and a few other gases. And half of the incoming solar radiation, called insolation, reaches the Earth's surface. So you can see here in this figure that we have sunlight coming down. Some of it gets immediately reflected by the clouds in the atmosphere. Some of it gets absorbed by the surface of the Earth. Some of it this heat energy gets absorbed by the clouds, and some of it gets reflected from a surface once it hits the surface of the Earth. Now, different surfaces on Earth will reflect light differently. Fresh snow, if you've ever gone outside on fresh snow without your sunglasses, you definitely know it can be very bright. That's because a lot of that sunlight energy that's hitting that fresh snow is getting reflected back upwards and into your eyes if you're looking down on it. So fresh snow is one of the highest reflecting surfaces naturally occurring on the Earth. Dense clouds also reflect a lot of sunlight before it actually gets to the Earth. Water can reflect also a lot of sunlight, and then as sand just reflects 20 to 30% of the light that comes in. So that's why sand will feel fairly warm, because a lot of the sunlight energy is staying in the sand. So if 20 to 30% is being reflected, that means that 70 to 80% of that sunlight is being absorbed. And so sand will feel warm generally because it's absorbing a lot more sunlight. Forests will reflect only a small amount of sunlight, so a lot of sunlight energy gets absorbed into forests. And water, when the sun is directly overhead, will reflect only 5% of the sun, but when the sun is low, water will reflect actually a lot more sunlight. And then dark soil will absorb or will reflect about 3% of the Earth's sunlight, so it will absorb a lot of sunlight, and therefore dark soil can feel very warm. So the sun warms our world, and it's particles in the atmosphere that keep us warm. So what happens is something called the greenhouse effect. And we talked about sunlight energy coming in, and some of that energy gets absorbed by the outer atmosphere by clouds, some of it comes to Earth and gets reflected. And we also talked about that there are a lot of different gases in our atmosphere. Now, carbon dioxide and other gases in the atmosphere, what they do is they absorb that sunlight energy coming in. And when they absorb that sunlight energy coming in, they keep it in our atmosphere. They prevent it from going back out again. And so sunlight energy comes in, some of it gets absorbed by the Earth, a little bit will get reflected by the Earth and sent back out. Some of it gets absorbed by the Earth. That keeps the Earth warm. Some of the sunlight energy gets absorbed by gases in the atmosphere. That helps keep the atmosphere and thus the Earth warm. And so what we see is something similar to if you build a greenhouse and you go into the greenhouse and it's warm, and sunlight energy is coming into the greenhouse through the walls of your greenhouse, and the energy from the sunlight goes in, but it can't go back out. And so since that sunlight energy gets trapped inside the greenhouse, it becomes very warm there. And our Earth is just like that. The layer of our atmosphere acts like a greenhouse. Sunlight energy comes in, but not very much energy goes out of that greenhouse atmosphere surrounding our Earth, and it keeps our Earth warm. If our atmosphere didn't capture this energy and have this greenhouse effect, then the Earth's average temperature would be about 21 degrees Fahrenheit, so below freezing, rather than the current 57-degree average temperature that we have. So if you could imagine, our Earth on average is 57 degrees Fahrenheit, it means that water is going to be a liquid on most of the Earth. If we did not have any greenhouse gases, we did not have an atmosphere keeping our planet warm, and we were at 21 degrees, then water would be in the form of ice most everywhere on Earth, and we would not have life as we know it on Earth. So the greenhouse effect again is a common term that describes the capture of energy by gases in the atmosphere. A lot of the incoming solar energy, so this energy from the sunlight, is used to evaporate water. And so as the sunlight hits our planet, it hits the water, and that sunlight energy helps to evaporate water. So that energy goes into changing water from a liquid form into the form of a gas. And so water evaporates into a gas, goes up into the sky, and that heat energy is stored in those water droplets up in the sky. Now, when the water droplets combine and they condense in the clouds and form precipitation or rain, then some of that energy is released. So the energy that's stored up in this water vapor in the sky is known as latent heat. So it's heat that is stored from the sun in the form of water. Ocean currents also modify our climate. Ocean currents redistribute warm and cold water around the globe, and you can see the lines here in red and blue showing how ocean currents move and how that water flows around through the oceans. So these currents modify our climate. For example, the Gulf Stream keeps northern Europe much warmer than northern Canada, and then variations in ocean salinity, so how much salt is in the water and how dense the water is, also help drive ocean circulation. If we look at how stable if we ask the question of how stable our climate is, it really depends on the time frame that you consider. So over centuries and millennia, so over millions of years, we know that climate shifts somewhat, but we usually don't expect a lot of change in the scale of our lifetime. The question is whether that's a reasonable expectation. And if climate does shift, how fast might it change, and what will those changes mean for the environmental systems we depend on? So when we talk about climate change, we have to look at first is, are the changes that we're seeing recently, the increases in temperatures, are those a normal part of the variation that occurs, or are those something out of the ordinary? The key to understanding climate and how it changes over time is to have data about what the climate has looked like in the past. And a lot of that data comes from ice cores. And so in Greenland and Antarctica and other places where cold is persistent and we have ice for a long period of time, we can take out ice cores and analyze those ice cores. So new layers will compress the lower layers of the ice, but in that ice there are still tiny air bubbles, and each air bubble is a tiny sample of the atmosphere at the time that snow fell. So it gives us data, the deeper down we go into the ice core, gives us data from further back in time on what gases were present in the atmosphere at that time. Climatologists have discovered that by drilling deep into an ice sheet, they can extract ice core samples that show how the atmosphere has changed over time. And here's a look at an ice core sample. This is Dr. Mark Twickler from University of New Hampshire holding a section of, so just a piece of a 3,000 meter core that was taken, and that 3,000 meter core records 250,000 years of climate history. So again, depending on how deep they go in that core that they drilled, they can look at the tiny gas bubbles in that core and analyze what the atmosphere looked like at that time. Now here's a look, if you do look at that core for that huge core, you can look back at the carbon dioxide. You can test those samples for the amount of carbon dioxide in those samples and look back over 800,000 years of data to see what the CO2 and temperature look like over millions and or over almost a million years, so 800,000 years. So these cores show us that the climate has varied dramatically over time. So if you look at the temperature and CO2 in those cores over time, you can see huge variations in the this is the CO2, and then variations in the temperature over the years. So we've seen huge cycles in temperature and CO2 in the atmosphere over that 800,000 years. What we can also see from this data is that temperature and CO2 are very closely correlated. So whenever CO2 goes up, temperature also tends to follow. And whenever we see drops in CO2, we also see drops in temperature. So from these ice cores, we know that CO2 concentrations have varied from between 180 to 300 parts per million in the past 800 years. And we know that today our CO2 concentrations are at 400 parts per million and rising about 2 parts per million per year. So they're about 1/3 higher than the Earth has seen in nearly a million years. So let's look at what causes natural climate swings. So we talked about in that last graph that we see these natural climate swings over time, and we'll look at why we see these climate swings. And so again, this is natural climate swings, not climate swings from man-induced causes. But every 11 years, we see an 11-year cycle on the sun's intensity. So there's this 11-year cycle of the Earth being a little bit closer to the sun and being a little bit further away from the sun, depending on the Earth's orbit. And so that's an 11-year cycle that we get a little closer to the sun, we get a little further away from the sun, and that causes minor climate changes. So not large climate changes, but a little bit of a climate change on an 11-year cycle. So things you'd see every decade or so in your lifetime. Now, more dramatic shifts are called Milankovitch cycles, and these are due to changes in the Earth's orbit. So it will change its orbit just slightly, the degree of the orbit, and we see these changes in the orbit every 100,000 years. And there are changes in the Earth's tilt, so variation in tilt, that we see every 40,000 years. And then the Earth sort of wobbles on its axis, and that cycle repeats every 26,000 years. So these are larger climate changes that you'd see every essentially 26 to 100,000 years. You'd have these different changes in the Earth's orbit and tilt and wobble, and those produce larger scale climate changes. So if you remember that last graph, how you see those major ups and downs in temperature, those are, for the most part, caused by these Milankovitch cycles. Another natural climate change that we see is called El Niño Southern Oscillation, or ENSO, and this is climate change that occurs according to oscillations or movements back and forth of the ocean and the winds. So trade winds will normally pile up warm water in the ocean around Indonesia. So in a normal year, you'll have a lot of warm water around Indonesia, and that creates the tropical monsoons that they normally get there. Now, every 2 to 7 years, the trade winds will weaken and warm water will sort of move like water sloshing back in a bathtub. The warm water will move, and surface water temperatures off South America will then warm up. And the clouds and rainstorms associated with warm ocean waters shift to the east. So normally we have the warm tropical monsoons here, but we get this shift to the east during the El Nino years. And this warm water releases so much energy into the atmosphere that weather changes all over the planet. We call this El Nino, and again, that happens about every 2 to 7 years. Some changes that we see during a strong El Nino is above average precipitation in the southern tier of the United States from California to the Atlantic coast. So along the southern portion of the United States, all across the whole US, we see much more rainfall, and then below average winter temperatures. So it gets colder and rainier during El Nino in the southern part of the US. Temperatures are warmer and typically drier than average in the northern part of the United States. So in the Pacific Northwest and Ohio and Tennessee valleys, rainfall is often below average and tends to be warmer. Now in the South America, areas like Peru and Chile and Ecuador tend to get record rainfall during El Nino years. So whether an area is drier and warmer or colder and wetter in an El Nino just depends on where in the world you are, but the El Nino does change weather all around the world, again, based on warm water sort of sloshing back and forth in the oceans every 2 to 7 years or so. Again, the big question that we keep asking is, how do we know that climate change is happening faster than usual? So we've looked at a lot of natural causes of climate change. We see that there are variations over anywhere from a few years to 100,000 years, and these changes occur naturally. But many scientists consider anthropogenic or human-caused global climate change to be the most important environmental issue of our times. And there's pivotal evidence that human activities are increasing atmospheric carbon dioxide from an observatory on Mauna Loa volcano in Hawaii. And so they've taken measurements they've taken constant measurements from 1958 into the present, looking at the average CO2 and monthly average CO2 and annual average CO2 and the temperature every 5-year average over this time period. And measurements show that CO2 levels are increasing at about 0.5% per year since 1958. This is called the Keeling curve, and it shows that CO2 concentrations have risen from 315 parts per million in 1958 to 393 parts per million in 2012. Because the climate's so complex, climate scientists from around the world have gotten together to collect and share data and try to make programming models to describe how the climate system works. And their evidence shows minor differences among the models, but there's no disagreement about the direction of the change. And the evidence shows unequivocally that climate is changing and that the global average is warming because of increased retention of energy in the lower atmosphere. So the different scientists, again, they've made these different models, and their models are showing that our climate is getting warmer and that it's getting warmer at an unprecedented rate. A little while back, something called the Intergovernmental Panel on Climate Change, IPCC, was formed, and this is the most comprehensive effort to date to look at the state of climate and climate knowledge and analyze research and look at trends in climate change. And the IPCC brings together scientists and government representatives from about 130 different countries with the aim of reviewing scientific evidence on the cause and the likely effects of human-caused climate change. In 2007, the IPCC issued its 4th report, and their conclusion at that time was that with about 90% certainty that observed climate change was caused by human activity, and subsequent reports have raised that certainty to 99%. So again, these are scientists and representatives from 130 different countries around the world. They're all getting together to try to look at how climate is changing and analyze that and study all of the research that's been done. And those are their findings currently, that they're 99% sure that climate change that's going on is caused by human-induced changes and not part of the natural cycle. That brings us to the year 2010, and as you can see, in 2010, the IPCC had made these predictions and saw that their predictions were much too conservative, that emissions were much higher than they anticipated. And so that's where we get this quote coming from at the beginning of the lecture that the International Energy Agency put out in 2010 that said the next decade's critical. And again, this was the slide at the beginning of this lecture saying if emissions do not peak by around 2020, the needed 50% reduction by 2050 will become much more costly. And in fact, the opportunity may be lost completely. And what we see currently coming up to the year 2020 now, so another decade almost later, is that this is a report put out by the United Nations Environmental Program, and they said that greenhouse gas emissions show no sign of peaking, and global carbon dioxide global carbon dioxide emissions from energy and industry increased in 2017, and that followed a 3-year period of stabilization. So the levels stabilized for a few years before that, and then they started increasing again in 2017. Total annual greenhouse gas emissions reached a record high and a record increase compared with the year before. So we needed to peak by around 2020 in order to prevent the costs from becoming exorbitantly high, and we are not seeing that peak at 2020 that they predicted 10 years ago that we'd need. Now, really the biggest problem here is that there's a lot of scientific consensus that there's a problem and that we need to find solutions to this problem and that there needs to be change. But the problem is that one, initial change is expensive and no one wants to make that upfront cost, even though the long-term cost may be incredibly severe. It's hard to convince countries, whether those are developing nations or developed nations, to take responsibility and make these changes. So climate control becomes a classic free rider problem in which nobody wants to take action for fear that someone else might benefit from their sacrifices. So it's one country having to sacrifice and say, we're going to make these changes. And typically what these programs want is for the more developed nations, something like the US, to make changes and become more to reduce emissions, and there's a lot of cost to that, and then they aren't expecting the same from third world countries because they don't have the money to generally make those changes. And so a lot of countries like the US pull out from these programs, not wanting to do that because they don't want to be the ones burdened with the cost. So there's a question about whether the sacrifices need to be as big as some policymakers suggest. So there's a chance that even some smaller changes could be really beneficial. And climate scientists point out that shifting our energy strategy from coal to things like wind, solar, and other greater efficiency things could produce millions of new jobs and save billions in healthcare costs associated with coal burning. But again, that initial change and that upfront cost is hard, and people and countries so far are some more willing than others, but a lot of times it's hard to convince countries to make those necessary changes, even though there's scientific consensus that we really need to make those changes and that there can be very devastating effects from not making those changes. So let's take a look at what the main greenhouse gases are. And the main greenhouse gases are carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O. And since pre-industrial times, the atmospheric concentrations of these gases have climbed by over 31% for carbon dioxide, 151% for methane, and 17% for nitrous oxide. And carbon dioxide is by far the most important of these because of its abundance and because it lasts for decades or centuries in the atmosphere. So the other gases tend to dissipate more quickly. Carbon dioxide lasts for a long time, so it has longer lasting effects on the temperature and changes in our climate. If current trends continue, carbon dioxide concentrations could reach about 500 parts per million, approaching 2 times the pre-industrial level of 280 parts per million by the end of the 21st century. So if you look here at our levels over since industrialization, this is what our levels have of all those 3 gases that we're talking about, the main greenhouse gases, have looked like. So we've seen since about the year 0 to about the time of the Industrial Revolution, around in here, that levels were pretty consistent throughout that time. And then once the Industrial Revolution hit, we started burning a lot of things like coal and other gases, that those levels of greenhouse gases at that point shot up significantly. Here's a look at some different charts from your textbook. And the one on the left here shows gigatons of carbon dioxide per year and that are emitted, and you can see in 1970 what the levels were like. In red is carbon dioxide, yellow is from fossil fuel use, yellow is carbon dioxide from deforestation, decay, and peat, and purple here is methane, and blue is nitrous oxide, and then this white is fluorine gas. And you can see how those levels have changed. The main thing that's changed is carbon dioxide from fossil fuel use that's being emitted into the atmosphere, and you can see how those levels have changed from 1970 to the present. And this is a look at what countries are the largest cause of the emissions worldwide of emissions of greenhouse gases. And so China is the largest emitter of greenhouse gases currently. US is coming in pretty close second, and then we have Western Europe and India and then here Japan and Russia, and then all other countries making up this amount here. So that just shows you, gives you a look at what countries are the largest emitters of greenhouse gases. Let's look next at what consequences we see. So what's likely to happen as it gets warmer? So if we continue to emit more greenhouse gases and the temperatures become warmer, what will be the consequence of that? And we know that it's now warmer than it has it's now warmer now than it has been in the last 2,000 years. And over the last century, the average global temperature has climbed by about 0.6 degrees Celsius or 1 degrees Fahrenheit. And global sea level has also risen approximately 20 centimeters or 8 inches in the past century. Some other things that are happening is permafrost is melting, houses, roads, and pipelines and sewage systems and transmission lines are being damaged as the ground sinks below the permafrost. So in the northern part of the globe, and Arctic sea ice is only half as thick now as it was 30 years ago, and Antarctic ice shelves are starting to break up. Now, if sea levels continue to rise, this is just a look at what the southern part of the United States, what the shoreline would look like if we had a 1 meter or 3 foot level of sea rise. And that's the change that they're anticipating by the year 2100. And if no action is taken, there may actually be a change of 2 meters or 6 feet or more change by the year 2100. And so if you see on here, this kind of gray line here is our current shoreline, and the green is what they are expecting the shoreline to look like by the year 2100. So losing all of this land here, going underwater, that would be with a 1 meter sea rise. That's sort of the minimum they're expecting, but they're expecting could be up to a 2 meter sea rise. This is what Florida would look like. So you'd lose this tip of Florida here. This gray line again is where Florida currently is. That would all go underwater, and you would just have the green part of Florida left. So there'd be large changes in land where the shoreline is, which would certainly put certain cities completely underwater. And that's one change that we'd be likely to see if temperatures keep increasing. Nearly all mountain glaciers are retreating rapidly, and many have disappeared entirely. Satellite images and surface measurements show that growing seasons are now as much as 3 weeks longer in a band across Eurasia, Northern Eurasia and North America than they were 30 years ago. So the longer growing season means it's warmer for longer, and by as much as 3 weeks. Droughts are becoming more frequent and widespread, and plants and animals are breeding earlier or extending their range into new territory. So these are all indicators that when we look at where plants and animals go and when they breed, they typically have patterns that we see over time, and those patterns are now starting to change. Coral reefs worldwide are bleaching. They're losing key algae, and so we're losing key coral reefs as well from around the world. We've also seen sharp declines in ice-dependent species, such as these penguins here, and some of which have lost half or more of their population due to loss of ice and loss of their habitat. Here's a picture from your text also from Glacier National Park, and you can see the same picture in the photos here in the early 1900s, and then presently, and you can see how the glaciers have changed from the early 1900s to now. So this was a glacier that normally was present year-round, and that is rapidly becoming smaller and smaller. As climate conditions change, that also changes where farming can occur and where different crops can grow. And the area in the lighter yellow here shows the area that's viable for wheat now, and then this darker orange shows the area that they anticipate being viable for wheat by the year 2050. So wheat production may need to shift entirely to Canada due to the climate and growing conditions not being appropriate for wheat where they currently are growing. So you may see changes in where crops are grown and where they can be grown, and wheat being one of our main staple grains for the country, that growing area could completely change. The IPCC is the group who is reviewing and analyzing all of the climate research that's going on. And one of their somewhat conservative estimates on how temperatures will change over the next 100 or so years is shown in this chart here. And so surface temperatures, and this is what the conservative estimate, are projected to rise sharply even under their conservative scenario, and that would assume that we adopt new energy technology, that we reduce fossil fuel use, and that we have a declining population after the year 2050. So even with all those changes in place, these are the changes that we would expect to see. And this is the average temperature change in degrees that you'd expect to see all across the globe. So a lot of where North America here and a lot of the main part of the area where people live, you'd expect to change anywhere from about 2.5 to 5.5 degrees warmer. And then the poles significantly changing, which would significantly melt ice levels and lead to increases in sea levels rising. Here's a look at what climate scientists are predicting we will see in terms of weather for, and this would be in the year 2100, what they're anticipating the weather would look like. And they're predicting that in the winter that we will see blue means more precipitation, brown means less precipitation. So in the winter, the northern part of North America, they expect to be wetter than usual in the winter, and then the further south you go down towards the southern part of the US and Mexico would be much drier than usual in the winter. And then in the summer, they're expecting most of North America to be much drier than usual, and except for as you go much further north toward the pole, then you would see wetter than normal in the summer. So those are just the changes that they expect to see with climate change. So it doesn't necessarily mean that you'll be warmer all year long. They're drier all year long. There's certain times of the year, like for example, where we live, that you're going to be seeing a little bit wetter than normal in the winter, but definitely drier than normal in the summer is what they're predicting. One important thing that they found in climate studies is that controlling emissions is a lot cheaper than the cost of climate change. And in 2010, there was a study done by Pew Trust that estimates the costs of lost ecological services by the year 2100. And the costs that they looked at include factors such as loss to agricultural productivity from drought, damage to infrastructure from flooding and storms, lost biological productivity, health costs from heat stress, and lost water supplies. So these are all factors when we talk about the cost of climate change. These are the things that they are looking at. And the Pew report found that climate change is likely to cost between 5 trillion and 90 trillion by the year 2100, and that's 5 to 20% of the global gross domestic product. So that is the cost that they estimate. That it's a large range, but that's what they estimate that all these costs will go up by if climate continues changing like it is. The Stern report estimates that there is a cost of only about 1 trillion, so 1% of the global domestic product, to avoid the worst impacts of climate change. So if we made changes to reduce climate change that cost about $1 trillion, then you could avoid having costs of $5 to $90 trillion later down the road. So it's a lot cheaper to spend this $1 trillion now than have to spend the $5 to $90 trillion later that would occur due to climate change. Let's look at next why there are disputes over climate evidence. So you've probably heard a lot of these things before, and these are some common things that you'll hear people come up with, the media come up with, and responses by climate scientists to these claims. So one claim that you might hear is that reducing climate change requires abandoning our current way of life. And the climate scientist's response to that is no, but it does require that we use different energy sources. So we may have to change our current energy sources, but we would not have to necessarily change our way of life, just change the way that we get energy. Another claim is that there's no alternative to current energy systems. And the climate scientists state that this is also not true because Europe and China are using different energy systems and having success with that. Another claim is that a comfortable lifestyle requires high carbon dioxide output, and data show that this is false. And again, a lot of this is that you could still have the same lifestyle, but by using alternative energy systems. And also natural changes such as solar variation, and this is another claim that natural changes such as solar variation can explain observed warming, and changes are slight to and do not coincide with the climate changes. These natural changes, things that occur naturally, like solar variation, those changes would make minor changes in the climate and wouldn't account for the large scale changes that we're seeing now. Another claim is that the climate has changed before, so this is nothing new. I think that sounds like a pretty good argument because there are major changes in the climate. In the past, it goes through cycles and it goes through extreme highs and lows. But the problem with this statement is that today's carbon dioxide levels exceed anything the Earth has seen for nearly 1,000,000 years. So if you look back at 1,000,000 years worth of data, we've never seen the carbon dioxide levels at the level they're at now. Another claim that people make is that temperature changes are leveling off, and this might be true on short time frames sometimes, but over decades, the trends in surface air temperatures and sea levels are continuing to rise. So we do see those highs and lows change every year, but in general, the trend is that they are increasing. Another claim is that we've had cool temperatures and snowstorms last year, not heat and drought. So there might be a year that you see something where the year is abnormally cold and compared to what you're used to, but there are regional differences in temperature and precipitation trends that are predicted by climate models. So we're going to have variation. We're going to have hotter years and colder years, but again, the overall trend is that the temperature is going up when you look at it on a worldwide scale. Climate scientists, another claim is that climate scientists don't know everything and they have made errors and misstatements. And so your textbook says that fraud in data collection is almost unheard of in science. The main goal of science, and when these people get together to evaluate, like the IPCC, when they evaluate research, they're evaluating whether it's quality research, whether it's done properly. And so the general consensus on all of the research that's been done, that they've analyzed, that they feel is good quality research, is showing that the climate is changing at unprecedented rates right now. Section 9.4 looks into solutions to the climate change problems, and former President Bill Clinton has argued that combating climate change doesn't have to mean economic hardship. In fact, it could be used as a big development stimulus and create millions of jobs and save trillions of dollars in foreign fuel imports. But again, change is hard, and making that change to existing jobs and existing systems is a hard sell for the public in general. And we'll look next at what are some of the strategies that we do have available. Many ways that we can control greenhouse emissions. We can reduce our dependence on coal, which produces more carbon dioxide per energy unit than any other fuel. We could institute fees for selling fossil fuels. These would help fossil fuel prices represent their many hidden costs. We can invest in new technologies and energy efficiency, and we can institute emissions trading by instituting a legal cap on emissions and then allowing companies to buy and sell shares with that total cap. Essentially, what this last option would mean is that companies would have a cap that they can't go over for emissions, this legal cap, so they'd be fined if they went over that amount, but they could buy and sell their emissions that they use or don't use with other companies. So say, for example, one company is way under in their emissions, they could sell the amount of emissions they don't use to another company, allowing that other company to go higher. And then that one company that was lower could make money from selling that, and the company that needed to have more emissions would just pay for those emissions. And so that would be one way to kind of put a cap across the country on what we want emissions to be. International protocols have tried to establish some common rules. So the first and across the globe to try to reduce emissions and control climate. And one of the first that was done was the United Nations Framework Convention on Climate Change in 1992, and the United Nations, so they had the United Nations Earth Summit meeting in Rio de Janeiro, and it set an objective of stabilizing greenhouse gas emissions. One of the next meetings in Kyoto, Japan in 1997 got together, and 160 nations agreed to roll back their carbon dioxide, methane, and nitrous oxide emissions by about 5% below the 1990 levels by the year 2012. China and India were exempted from this agreement because the US were exempted because they were developing nations, and so in this protocol, nations with less economic resources were exempted from this. So they tried to get the countries who would be able to afford to make these changes stand up and start making some positive changes. The US never agreed to this, and so they weren't a part of this, but this was called the Kyoto Protocol, and that was in 1997. Then more recently, in Paris, France in 2015, they had what was called the Paris Agreement, and 175 countries signed an agreement to combat climate change and adapt to its effects with enhanced support to assist developing countries to do so. So again, this was more the developed countries would start making these changes and take the brunt of the cost of this and help developing countries to do this. So there was more pressure put on the developed countries and not as much on the developing countries. And again, this was called the Paris Agreement. More recently, in 2017, President Trump announced his plan for the US to leave the Paris Agreement. And so that hasn't happened yet, but that was the plan that was stated in 2017, was that the US would not be part of that. And this was important because the US is a big global player, both economically and just as being an example. But that was the decision made at that point, was for the US not to be part of the Paris Agreement. So again, these are just some major different meetings that have occurred that have sort of changed the course of where climate change is going and that are important in the climate change world. One alternative approach to just saying emissions need to be reduced by a certain amount is to use something called a wedge approach. And in the wedge approach, you break down a large problem into smaller bite-sized pieces. And the idea is that a country starts making small changes in things like vehicle efficiency or less driving, building efficiency and insulation, power plant efficiency or carbon capture, alternative energy sources, and protecting forests and soils. And they make little changes in all of these areas rather than saying there has to be a big change in or complete change towards no emissions in any of these areas. There's just small changes. And over time, the effect of those small changes become large as each year the impact of that reduces emissions. And so you could have a large impact over time by starting small and then slowly getting bigger. And there was a paper by Pakala and Sokolov who described 14 wedges. These are the wedges here, and each wedge represents 1 gigaton or 1 billion tons of carbon emissions avoided by the year 2058 for each of those wedges out of the 14. So that's just a different approach to how a large problem might be solved. Accomplishing just half of these wedges would level off our emissions, and accomplishing all of them could return levels to well below those envisioned in the Kyoto Protocol. There are different local initiatives everywhere around the world, so different countries are doing initiatives differently. Britain has already started to substitute natural gas for coal, promote energy efficiency in homes and industry, and raise its already high gasoline tax to try to discourage gasoline use. New Zealand Prime Minister Helen Clark several years ago pledged that her country would be the first to be carbon neutral. Germany has reduced its carbon dioxide emissions at least 10% by switching from coal to gas and by encouraging energy efficiency throughout society. Denmark now gets 20% of electricity from windmills. So these are some changes that have currently been made and that have had a positive impact on reducing emissions. Now, it's easy to think of reducing carbon emissions as a worldwide problem or even a nationwide problem, but individual actions are also extremely important because individual actions can have tremendous impacts on climate change, as our actions are multiplied by millions of others who make similar decisions. So if all the millions of people in even just our country started making a little bit wiser decisions in terms of emissions, it could have a huge impact when you look at that across the whole country. This graph shows a summary of which individual steps would make the most impact. So if you're wondering what you could do that would make the most impact, the largest change that we could make as individual people is having a more fuel efficient vehicle. Carpooling would be another one. So you're driving in one car instead of two. Weatherization of your house to make it more energy efficient. Just driving behavior can actually make a big difference. So not accelerating as quickly and things like that can actually reduce your emissions. Having more energy efficient appliances, and then you can look at the list of different things here, and all of them, even though these impacts are small, if you think if you did these, or if everyone did these throughout the day, like turning down the AC or the water heater a little bit, there's different things that you could do that would be relatively small changes. Wouldn't have to be huge changes, but little bit smaller things that could have a big impact if everyone made some small changes. Another option to reduce carbon dioxide emissions actually going into the atmosphere is to store carbon dioxide. So it is possible, but it is very expensive to store carbon dioxide by injecting it deep into geologic formations. Since 1996, Norway's Statoil has been pumping more than 1 million metric tons of carbon dioxide per year into an aquifer 1,000 meters below the seafloor. And this pressurized carbon dioxide actually enhances oil recovery and saves on carbon taxes in Norway. So they're reducing their carbon emissions by pumping the carbon dioxide into the ground, into these aquifers of water. Around the world, deep briny aquifers could store a century's worth of carbon dioxide output at current fossil fuel consumption rates. So that is feasible, that we could just take all of our carbon emissions and pump them into the ground, but it is expensive to do that. Here's a figure from your text on 3 different ways that carbon capture technology can occur. And the first is that you can pump carbon dioxide so you have a power station here, it's emitting carbon dioxide, you can capture that emitted carbon dioxide and you can pump it into old coal fields. That makes methane come out of that coal field. That methane could be used then as a fuel source. So that's one option, to pump it into old coal fields. Another option is that you could take the CO2 emitted from that power station and pump it into saline aquifers and store it down in saline aquifers. And a third option is that CO2 can be pumped into oil fields to help maintain pressure and make extraction easier. So you can pump it into oil fields. Those are 3 different ways that carbon capture technology can work. But again, for a power station to do this and set up this whole process and pump it down there is very expensive. So it's a good way to reduce emissions, but it is very costly. So in conclusion, to go over briefly what we covered today, temperatures are now higher than they have been in thousands of years, and climate scientists say that if we don't reduce greenhouse gas emissions soon, the drought and flooding of cities may be inevitable. So extreme weather changes may occur, and not always just warmer and drier, but you can have huge droughts and huge floods occurring in different parts of the world due to the changing weather. Exhaustive modeling and data analysis by climate scientists show that these changes can only be explained by human activity. So we have never seen in the history of the data that we are able to look at, we've never seen changes occurring at such a drastic rate, changes in carbon dioxide ever being this high or ever going this high this rapidly. So they think the only way that you can explain this is by human activity and all of our carbon dioxide emissions that we're pumping into the atmosphere. And lastly, the stabilization wedge proposal is a list of immediate steps that could be taken to accomplish needed reductions in greenhouse gases. And again, the wedge approach is that you start with small changes and the impact of those changes grows larger and larger over time. So let's go back over our learning outcomes from the beginning. Our first learning outcome was to understand how the troposphere and stratosphere differ. And so here is our picture of our different layers of the atmosphere. So remember, there's 4 layers of the atmosphere: troposphere, stratosphere, mesosphere, and thermosphere. Most of our weather occurs down here in the troposphere. And so that's the layer closest to the Earth. And then the stratosphere is where our ozone layer is, and that's the next layer up. Our next question, our next learning outcome was to understand what are some of the factors in natural climate variability. So we talked a lot about in this lecture about natural changes in climate that we see occurring over time, and then man-induced changes in climate. So what we're going to look at now is the natural climate factors, so ways that climate changes naturally without any impact from human activity. So these natural factors in climate variability include changes in ocean currents. So if you remember, warm water and cold water moves back and forth, and that causes changes in the climate over a short scale of time. There are also the El Nino changes, and those are due to changes in the trade wind. So remember, that's the kind of sloshing of warm water back and forth, changing where those monsoons occur and also where droughts occur. So every 2 to 7 years or so we have the El Ninos, and those produce changes in the climate as well. We have 11-year cycles in the sun's intensity based on where the sun is orbiting, where the Earth is orbiting compared to the sun. And so whether the Earth is closer or further away from the sun changes the climate. And these are about 11-year cycles. We also have the Milankovitch cycles, which are looking at variations in orbit and tilt and wobble of the Earth, and those cause 20 to 100,000 year cycles changes in climate. So these are 3 different things: ocean currents, El Ninos, cycles in sun's intensity, and Milankovitch cycles that cause natural changes in the climate. Third objective is to explain the greenhouse effect and how it's changing our climate. If you remember, the greenhouse effect is where sunlight comes into the Earth, bounces back off surfaces of the Earth or back off different particles that are in the atmosphere. And when it hits different particles in the atmosphere, that causes the sunlight energy to bounce back down to the Earth. So it sort of the sun's energy gets trapped in this layer around the Earth in the troposphere, in that first layer of atmosphere, and it acts like that troposphere acts like a greenhouse around the Earth. So it's a natural way that the Earth keeps warm. Otherwise, we would be at freezing temperatures all the time if we didn't have the greenhouse effect. So that's a natural occurrence. What's changed with our greenhouse effect is that if you look at our carbon dioxide levels recently, they have gone from ranging in this range here from a little below 200 to close to 300 over time, and now we are seeing carbon dioxide levels in the atmosphere at about 400 parts per million, so higher than we've ever seen them. And the more carbon dioxide molecules there are, the more intense the greenhouse effect is and the warmer temperatures we get. So that is how the greenhouse effect is changing our climate, is that we have more particles in the atmosphere trapping heat and making the Earth on average warmer. I think one of the biggest questions people ask is our next objective here: how do we know the nature and cause of recent climate change? So how do we know that it's human induced and not due to natural causes? We've covered that a little bit, but if you look at, again, our changes in carbon dioxide in the atmosphere, if you study those ice cores and look at how much carbon dioxide was in the atmosphere over the past about million years, we've never seen levels that have risen as quickly or ever been as high as they are currently. And one really good indicator is that since the before the Industrial Revolution, our emissions levels in the atmosphere were pretty constant. They went up and down a little bit, but they were fairly constant. And then as soon as you hit the Industrial Revolution here, the amount of emissions in the air skyrocketed, and our temperatures also started changing in correlation to that. So we know that the recent changes are not natural because we're about 99% sure that they're not natural, because we've never seen changes occur this quickly, and usually the changes occur much more slowly over time, and we've never seen the emissions levels and temperatures be as high as they are now. Our fifth objective is to list some of the effects of climate change, and one is that we're seeing a reduction in the ice around the polar ice caps and a reduction in the species that are dependent upon that habitat, like the penguins. So as much as 50% decline in these populations have occurred recently. We're seeing a retreat of a lot of the mountain glaciers, so we're seeing those changing at a rapid rate, growing smaller. We are seeing changes in temperature and precipitation. So here's changes in precipitation that have already been occurring, and then this graph shows the projections of what we expect to occur, but we are seeing changes in the areas where we live in the summers becoming hotter and drier and winters becoming wetter. And then changes in temperature. This chart shows changes in temperature that we are currently seeing and that we project to see into the future. So those changes in temperature and precipitation obviously are going to change where plants can grow. So areas that are viable for certain plants are starting to change, and they predict this change to continue. And so areas that are viable for the same crop to be moving northward. So those are a few of the changes that we have seen so far and predict that will continue changing over time. Our last objective is to list some of the strategies for minimizing global climate change, and we have the strategies mentioned in this wedge approach. Those are things like vehicle efficiency, less driving, building efficiency and insulation, power plant efficiency, switching fuel type, carbon capture technology, which is shown here, alternative energy sources such as wind and solar, and then protecting forests and soils. So those are some different strategies to minimizing global emissions. Some individual strategies are having more fuel efficient vehicles, carpooling, weatherizing houses, changing driving behavior, having more efficient appliances, such as heating and air conditioning, and adjusting the thermostat to not come on as frequently, changing furnace and AC filters, routine car maintenance, efficient water heaters, line drying laundry, turning down the AC, and low flow shower heads. So those are all some different individual changes, with the ones at the top being the most effective changes that we could make as a society. Okay, that's the end of our Chapter 9 lecture. Next week we'll be looking at Chapter 11 on water resources and pollution. Let me know if you have any questions as you go about your week.